Okay, in this video we're going to begin section 7.2, and that's verifying trigonometric identities. In this section we're going to study techniques to verify trig identities. In the next section we're going to study techniques to solve trigonometric equations. The key to verifying identities and solving equations is the ability to use the fundamental identities and rules of algebra to rewrite trigonometric expressions. And this helps a lot too in calculus. You know, in calculus we might have some trig expression that's pretty complicated that we want to perform some operation on. And it really helps if we can simplify that trig identity first and then perform the calculus operation on it. Remember that a conditional equation is an equation that is true for only some of the values of the domain. For example, the conditional equation, the sine of x equals 0, is true for n times pi, like 1 pi, 2 pi, 3 pi, 4 pi, where n is just some integer. When we find these values, we are solving the equation. On the other hand, an equation that is true for all real values in the domain of a variable is an identity. For example, the familiar equation, sine squared equals 1 minus cosine squared. You know, that's our Pythagorean identity, sine squared plus cosine squared equals 1, and we subtracted cosine squared from each side. This is true for all real numbers of x, so this is an identity. So although there are similarities, verifying that trigonometric equation is an identity is quite different than solving an equation. There is no well-defined set of rules to follow to verify trig identities, and the process is best learned by practice. You know, a lot of it's trial and error, but there are some vague guidelines here to work on these trig identities. First one, work with one side of the equation at a time. It's often better than working with, or it is often better to work with the more complicated side first. Look for opportunities to factor an expression, to add together fractions, square a binomial, or create a monomial denominator. Look for opportunities to use the fundamental identities. Note which functions are in the final expression that we want. Sines and cosines pair up well. Secants and tangents pair up. Cosecants and cotangents are good pairs. If the preceding guidelines do not help, you know, a good rule of thumb is try to convert all terms into sines and cosines if you possibly can. Always try something. Even paths that lead to dead ends can provide insights or give you a clue as to maybe where you took a wrong turn, so you can go back and take the right turn. So here in example 1 it says verify the identity. Secant squared minus 1 divided by secant squared is the same thing as sine squared. So I'm going to rewrite it here. We have secant squared of theta minus 1 over secant squared of theta is equal to sine squared. So one of our general guidelines here was work with the more complicated side first. So I'm going to take this left side and I'm going to try to turn it into the right side. And whenever you see a trig function squared, always think about the Pythagorean identities. So my first thought is to go after this secant squared minus 1. Can I replace secant squared minus 1 with something else? So let's see, here's our Pythagorean identities. Here's secant squared. Secant squared, if I minus 1 from each side, that would give me secant squared minus 1, and that's equal to tan squared. So could I replace this secant squared minus 1 with a tan squared of theta over secant squared of theta? Is that going to help, or you know, maybe this is a wrong term? We'll try to figure it out. So let's see, can we rewrite tangent as something? Well, tangent is sine over cosine, and here they're both squared. Tangent squared is sine over cosine. Tangent squared would be sine squared over cosine squared. And that's divided by secant. What's another way to write secant? Well, that's 1 over cosine squared. So now we have a fraction divided by a fraction. We could invert and multiply. So I could bring this 1 over cosine squared up and make that cosine squared over 1. Aha, look at that. On this diagonal, the cosine squareds will cancel, and we're left with sine squared over 1, which is exactly what we had over here, you know, the goal we wanted to get to. So let's see, we figured it out. Is that the only way to do it? Absolutely not. Oops, went a little too far there. Okay, let's look at an alternate way to do this. You know, the way we just did is absolutely fine. Here's another one. If I concentrate just on secant squared of theta, well, I can replace secant squared of theta with 1 plus tan squared. So I'm going to take this secant squared and replace it with tan squared plus 1. So that becomes a tan squared plus 1, and I still have this minus 1. And that's also still over secant squared theta. So let's see here. Now again, this plus 1 and minus 1 are going to cancel, and we sort of get to a step that we had in the last way we solved this. You know, here was our tan squared, and that was sine over cosine, both squared, divided by secant squared, which is cosine. If that's 1 over, or that would be cosine squared, so we bring it up and make it, well, secant squared is 1 over cosine. Bring it up and flip it. Cosine squared over 1, we get that cancel, and just like last time, we're left with sine squared. Okay, is there another way to solve it? Well, sure there is. Another way to look at this, when we have a single denominator and a two-term numerator, break it up. So my first term is secant squared, and I'm going to put that over the denominator, secant squared. Minus 1 is my second term, and I'm going to put that over the same denominator, secant squared. So it's here, secant squared over secant squared is 1, minus 1 over secant squared. Well, secant squared, or secant is a reciprocal with cosine, so 1 over secant squared we can replace with a cosine squared. And if we go back to the Pythagorean identities, again, here's a cosine squared. If I subtract cosine squared from each side, I'd get sine squared equals 1 minus cosine squared. So this 1 minus cosine squared I can replace with sine squared, which is where we wanted to get to. So there we went through 3 different ways to solve that first verification of an identity. Example 2. Okay, let's go back to those guidelines real quick. Where was it? Add fractions. You know, that's a guideline for trying to simplify these. And here we have 2 fractions on the right, 1 over 1 minus sine alpha plus 1 over 1 plus sine alpha, and we want to verify that that's the same as 2 secant squared of alpha. Again, we're going to start working with the more complicated side first. So if I want to add fractions, of course I need a common denominator. And it's not always the least common denominator, but one that will always work is to multiply the denominators we have. So I'm going to FOIL those out. Oops. I'm going to FOIL these out. So 1 times 1 is 1. And then we would have a plus sine of alpha, and then our inner terms would be a minus sine of alpha, so those will cancel. And then we're going to have sine of alpha times sine of alpha is sine squared of alpha. What would our new numerators be? Well, we multiplied this denominator by 1 plus sine alpha, so I got to multiply this numerator by the same 1 plus sine alpha. And I'm going to add to that, you know, careful, if that was a minus, we'd want to make sure to put this in parentheses because we would have to distribute that minus. But since it is a plus, we don't really have to worry about that. This denominator we multiplied by 1 minus sine alpha, so we multiply the numerator by the same 1 minus sine alpha. Well, let's see if anything cancels. Plus sine alpha and minus sine alpha go away. So our numerator is 1 plus 1 is 2. That looks a lot like the 2 we're going to need here. But how can we turn this denominator into secant squared? Again, I see a squared, so I think Pythagorean identities. 1 minus sine squared I can replace with cosine squared by the Pythagorean identity. And then, if I want to think about it this way, break that apart. I'll have 2 times 1 over cosine squared of alpha. And cosine squared is the reciprocal of secant squared. So I can replace 1 over cos squared with secant squared alpha. 2 secant squared alpha is exactly where we wanted to get to. And that's the only way I've found, but there might be more than one way to turn that into what we have on the left. So here on the left-hand side, we have 2 binomials that looks like we're multiplied, and we want that equal to negative tan squared of x. Now you might be tempted to, start foiling this out as soon as you see 2 binomials, but that's going to make a mess. We're going to have a tan squared times a cosine squared, and a minus a tan squared, and a plus a cosine squared, a bunch of stuff. So let's see if we can simplify it instead of multiplying. Let's see, tan squared plus 1, we can replace that with secant squared by the Pythagorean identities. Cosine squared minus 1. Now let's see here, I'm going to abbreviate this, but sine squared plus cosine squared equals 1. We want cosine squared minus 1. So if I subtract the 1 from each side, I'll have a cosine squared minus 1. And I'd want to move the sine squared to the other side, and it would become negative. Subtract it from each side. Negative sine squared x. So we can replace this cosine squared minus 1 with a negative sine squared of x. See, the whole point is to get this to negative tan squared. And the first thing I think of when I think of tangent is sine divided by cosine. Well, I have a sine. Can I make this into some form of cosine? Well, sure. Secant is reciprocal with cosine. So secant squared is the same as 1 over cosine squared. And then I'm going to multiply that by, I won't change this at all, negative sine squared over 1. If I multiply straight across, I'll get negative sine squared over cosine squared. Sine squared over cosine squared we can replace with tangent. Negative tangent squared of x. And there we go. Exactly where we wanted to get to. So here's 3 problems to practice with. Let's see if I can give a hint here. We're multiplying a couple things together. So you might want to look at your reciprocal identities. Neither of them are squared, so think about reciprocals. What can you replace those with? If you can, turn everything into sines and cosines. In number 15, we're definitely going to want to play with our trig identities, Pythagorean identities. Over here, we only have a sine squared. Here we have a sine squared. See if you can take this cos squared of beta and replace it with something from a Pythagorean identity. And the same thing for this unnumbered one down here. Take this secant squared of z and replace it with something. Again, maybe a Pythagorean identity, because all we want when we're done is tangents, tangent squared. So take those hints, take your formula sheet, pause the video, try to figure out how to turn the left side into the right side here on number 1. Here I'd turn the left side, work with the left side, turn it into the right side. And it probably doesn't matter which one you do here. When I solved it, I played with this side, the left side, and tried to turn it into the right side. So pause the video, try the problems, come back and see how you did. So the first one, again, there's nothing squared and we're multiplying a couple things. My first thought is reciprocal identities. I can change secant into 1 over cos of y. We already have a cos, so let's try leaving that alone for now. Cos of y over 1. Aha. On the diagonal, those are going to cancel out, or we could multiply across, and we'll get cos of y divided by the cos of y, and that equals 1, just like where we were trying to get to. So that one was pretty straightforward. In number 15, on the left we have sine squared and cosine squared. Over here we have sine squareds, and we have 2 of them. So maybe this sine squared we want to leave alone. But what can we replace cos squared of beta with? Well, by a Pythagorean identity, that is the exact same thing as 1 minus sine squared of beta. And then we still have this minus sine squared beta. Well, 1 minus sine squared beta minus another sine squared of beta. It's like 1 minus x minus x. Minus x and minus x is minus 2x's. So here we have minus 2 of these sine squareds of beta. Just like what we were trying to get to. 1 minus 2 sine squared beta. And we'll use a similar technique for this last one. Again, on the right, we only have tan squareds. Over here, we only have 1 secant, and it's negative. So we could approach this by taking this secant squared z and replacing that with a 1 plus tan squared z. And out front here, we still have our 2 minus. Well, 2 minus 1 is 1, and then we have our plus. Well, excuse me, we distribute that negative, and that would be minus tan squared z. Just like what we were trying to get to. And you don't have to start on the left. They say the more complicated side first. I'd say these are about equally complicated. We could leave the 2 minus secant squared z alone and have on the other side 1 minus, what can we replace tangent squared with? Tangent squared, if we move this over, would be secant squared minus 1. So we're going to replace this with secant squared of z minus 1. Distribute the negative, this will be a negative secant squared, and that will become a positive 1. Now I can eliminate my parentheses. So we have a 1 plus 1 is 2 minus secant squared z, just like we have on the left. The homework for this section is 555, number 1, 3, 4, 6, 7, 9. When you're solving these, especially the even ones, make sure to show your steps. The odd number ones are in the back of the book, but I want to see the work, the steps to get from where you're starting to where you end.